Okay. Okay, so now what I want to do is talk about the structure theorem for finitely generated abelian groups. One way to think about this is like kind of like linear algebra almost. So to think about this in linear algebra terms, a theorem of linear algebra says that if V is finite dimensional and V is like a vector space over the real numbers, then V looks like Rn. Okay, or in other words, like every finite dimensional vector space has a basis. Okay, and what we're going to see is that every finitely generated abelian group, well, it doesn't exactly have a basis, but like almost. So we want to find a basis for abelian groups. The difference is we don't have scalars to work with, we just have integers, but you can still do a lot. Okay, so you have a few definitions. Let's say Z to the R, which is just R copies of Z, Cartesian product. This is called the free abelian group on R generators. Okay. Another definition is that if G can be generated by A1, A2, up to AR, for some R greater than or equal to 1, and A1, A2, up to AR in G, then G is called finitely generated. Okay. To talk about finitely generated groups, well, there's a lot of groups that are finitely generated. Just some quick facts about them. Any finite group is finitely generated. Right, because G is just generated by all of the elements of G. And if G is a finite group, this is a finite set of generators. And there's some infinite groups that are finitely generated too. One example would be Z to the R. Z to the R is finitely generated. to think of a non-finitely generated group, well, the simplest example I know would be the rational numbers. Q is not finitely generated. Good. Just to give you an idea of some different things that are finitely generated. Okay. So our first proposition, let A be an abelian group generated by A1, A2, up to AR and A. And there is an onto homomorphism phi from Z to the R to A. And then the definition is just send N1, N2 to NR to A1 to the N1, A2 to the N2, up to AR to the NR. Okay. In the notes, I now see that there's a typo. I say if G is any finitely generated group. This is true, but it's only true for abelian groups. Sorry about that. Okay. So we have an onto homomorphism from Z to the R to A. I mean, if this was linear algebra, this would actually be an isomorphism, but it's not exactly. This homomorphism is not necessarily one-to-one. Okay, and how much is it not one-to-one? Well, we have a theorem to tell us this. Theorem. Okay. Let A be a finitely generated abelian group. Then there exists R and S greater than or equal to 0 and integers D1 dividing D2 dividing all the way up to DS, all greater than or equal to 2, such that A is isomorphic to a direct product, Z to the R times Z mod D1 Z times Z mod D2 Z, etc. Good. Okay. Not only that, but these integers are like the integer R And these integers, the di's, they're unique. Okay. So, and then in the these numbers have names. So R is called the free rank of A. Think of that like the dimension of a vector space, and D1 up to DS are called the invariant factors of A. Okay. Just as an example, we have if G is C3 cross C5, then G is actually isomorphic to Z mod 15Z. So the free rank of G is 0. The invariant factor of G is D1 equals 15. Another example, if G equals C2 cross C2, the free rank of G is 0 again, and the invariant factors of G are D1 equals 2, D2 equals 2. Because this is isomorphic to Z mod 2Z, this is isomorphic to Z mod 2Z, so we have two copies. So we have G isomorphic to Z to the 0 cross Z mod 2Z cross Z mod 2Z. And here the condition is that D1 has to divide D2, which is satisfied. As another example, we could do C2 cross C2 cross C3. Again, the free rank is 0. And actually we have C2 cross C3 is isomorphic to C6. So, or in other words, Z mod 6Z. So we have G is isomorphic to Z mod 2Z times Z mod 6Z. So D1 equals 2, D2 equals 6, and here we have 2 dividing 6, so that's what we want. Oops. Okay, so our next assignment will be assignment 5. And then on assignment 5, I'll just try and put a few questions to do with this structure theorem. Oh yeah, and I wanted to hand out assignment 5 on Monday. So I hope that's okay. Okay. Okay, so right. Sorry. Okay, sorry about that. So let's see. The next thing, so just following along with the notes. Our kind of last topics of group theory are the following. You have the Jordan-Holder theorem. And we have the topic of solvable groups. Okay, so just for time, we're still going to state the basic properties of the Jordan-Holder theorem and everything, but we're not going to prove it. So for time reasons, we're going to skip the proof of this. And then we'll get to do all the things as solvable groups, and that's the end of group theory. Okay. So we should be able to do this today once we skip the proof of it. Okay. Okay, so there's another thing about, yeah, so let us take another 5-minute break. When we come back, we'll talk about the Jordan-Holder theorem. Okay. Okay.